SwayamPrabha. Digital India. Educated India.
Welcome to this lecture on the use of MATLAB for doing inverse dynamics. In the last couple of classes, what you looked at is how to derive the dynamic equations of a manipulator. And we started off with the Lagrangian-Euler formulation, then we looked at Newton-Euler formulation, and then after that we looked at trajectory planning. Right. So today we'll see that if you want to write the equation of dynamics by hand, it is very cumbersome. Okay, for a 2 degree of freedom manipulator is still okay. But if you want to do for a 6 degree of freedom or a 10 degree of freedom, then it's very cumbersome and there is a high chance you'll make a mistake. So a better way would be to write a MATLAB program to do dynamics. And today we'll be looking at inverse dynamics, that is given the kinematic parameters, the lengths of the links, the mass properties, the inertia properties, and then given the time for which it is going to move from the initial position to the final position, how to generate a trajectory and putting that into the dynamic equations, how to derive the torques. So that is inverse dynamics. So we have to find the position, velocity and acceleration at every instant, put it in the dynamic equation and get those get the torques at those respective instants of time. Okay, so today we'll look at inverse dynamics using MATLAB. Okay, so today's we are going to look at inverse dynamics using MATLAB, and in the last couple of classes we have looked at how to write the dynamic equations, and then after that we looked at trajectory planning. So today we'll look at inverse dynamics using MATLAB. So let me formulate the problem like this, that we have a two-link manipulator. So this is my two-link manipulator. This is one link and this is another link, and the link lengths are L1 and L2, and there are two revolute joints. So this is 2 degree of freedom and this is a 2R manipulator system, and the mass is acting at the center at M1. So it is acting at L by 2, and the second mass here is acting at is M2, is acting at L by 2. Okay, and these are revolute joints. And now in terms of the DH parameters, okay, we can write the alpha 1, alpha 2 is equal to 0 because it's a planar manipulator. D1, D2, the offset angles are also equal to 0, and the link lengths A1 is equal to A2 is equal to L, and theta 1 is one angle which is a variable theta 1, and the other angle is theta 2, and these two are the variables. Okay, so we want to write the dynamic equation today of this two-link manipulator system, which will go from an initial position to a final position, and we want to find what are the torques acting at the joints. Now what are the two variables, theta 1 and theta 2? Okay, and we also have to specify the time of motion. So time of motion has to be specified. Okay, now in the last couple of classes we have derived the dynamic equation using Lagrangian-Euler or Newton-Euler. So in this particular case we are using Lagrangian-Euler. So here we are derive using Lagrangian-Euler dynamics, and if you write our equation, our dynamic equation using Lagrangian-Euler, then the final equation comes out in this form. For this manipulator it will come in this form. Okay, that means tau 1 tau 2 is equal to the D matrix, which is the inertia matrix, into the gravity. So d theta, this is my gravity, sorry, this is the acceleration, theta double dot in terms of t. This is my c theta dot theta, which is the Coriolis and centripetal force, and this is my sorry, this is my h. The way we have written it is h, and this is my c vector, which is the gravity vector, which is theta. Okay, so we have the three components of this dynamic equation, and they are the inertia term. In short form, I can write it as tau is equal to d into theta and theta double dot into t plus h theta dot into theta plus c into theta. Now what are the variables here? You can see that m mass is known, L is the fixed length. So what is the variables is theta double dot, theta dot and theta. So if I want to find what is the torques acting at the joints, I have to supply the joint position, velocity and acceleration at different instants of time. And for doing that, I have to fit a trajectory onto this joint angles, which will take it from one position to another position. Okay, so essentially what we are doing is, what you see is that in order to do the inverse dynamics of this equation, you also have to generate a trajectory. So you have to do trajectory planning also. Okay, so how do we start? Now let me write the dynamic equation like this: what is known and what is not known. So let me change the color. So what is known, tau of t, tau is equal to d into theta, theta double dot plus h, theta dot theta plus c into theta. Okay, this is my dynamic equation. Now let's take the example that this two-link manipulator that we just saw here. Okay, we just saw this two-link manipulator which we are trying to, I am going to write it, I'm going to make it simplify this, and I'm simply going to draw it like this. Okay, so there is a initial position. So this is my initial theta 1, theta 2. I'm going to define theta 1, theta 2. So this is my 0, 0 initial position, and I'll take it to some final theta 1, theta 2. Okay, so from here maybe it will go there, just for example. Okay, so where this is equal to 40 degrees and this is equal to 60 degrees. Okay, so after giving these parameters, the kinematic parameters, and then looking at the inertia parameters, then what we need to do is to define the time of motion. So let's say it goes from here to here in time t seconds. We have to define what is t. Okay, so what is it that we have to supply here? We said that the manipulator has to go from here to here in time, let's say time is t. Okay, now theta 1 from initial value int to a final value, theta 2 will go from an initial value to a final value in time t. Okay, the time has to be same. Why the time has to be same? Otherwise it will jerk. So the time of motion for both the joints, the start and the stop, should be simultaneous, should be same. Otherwise what will happen, if one joint is moving, the other joint is not moving, then it will be subjected to subjected to dynamic forces, which is going to result in a kind of a jerk. Okay, so if you look at a robot start and stop, it always starts and stops at the same time, all the joints. So for a robot, start and stop is at same time for all joints. Okay, so this is something that is to be noted. Otherwise there will be a jerk on the system. Now we have defined our initial and we have defined our final. Now in our dynamic equation here, what is the input that we have to give? We have to give theta, theta dot and theta double dot. Okay, so now we know the initial point, we know the final joint angle, we know the time for which it is moving. So what we can do is we fit a trajectory. So theta 1 t is equal to a naught plus a1 t plus a2 t squared, okay, plus a3 t cube. This is trajectory planning. We have looked at it in the last class. Now if I take the derivative of this, theta 1 dot is equal to a1 plus 2a2 plus 3a3 t squared, and theta 1 double dot t is equal to 2, sorry, there is a t here, so it is equal to so this is equal to, if I take the derivative one more time, this becomes equal to is equal to 2a2 plus 6a3t. Okay, so this is my position, this is my velocity, and this is my acceleration. Okay. Similarly, this will be for theta 1. Okay. So similarly, I'll have a set of equations for theta 2. So theta 2 also will be having theta 2t is equal to, let's call it a naught plus a1t plus a2t squared plus a3t cubed. Okay, this is another set, and from here we can get theta 2 dot, and we can get theta 2 double dot. Okay, simply by taking the derivative. Okay, so after getting this, what we need to do is we need to find the trajectory, which means solving for theta 1, we need to solve a0, a1, a2 and a3, the coefficients. Okay, we need to find this. Now you know how to find this from trajectory planning that was taught in the last class. Okay, so given initial value, so at theta 1 equal to 0, the position is 0. At theta 1 equal to final tf, or it will be at some location, let's say 40 degrees, just for example. And velocity is theta 1 at 0 is equal to 0, and theta 1 dot at time final is also equal to 0. So this one set of constraints, okay, for finding theta 1. Similarly, we can also find for theta 2. Okay, so for corresponding theta 2, for this we can find these parameters by these constraints. And similarly, for theta 2 also we can find by putting this constraints, we can find what will be the coefficients a0, a1, a2 and a3. Right. So now we have been given the time. So this is our time. Say I'm just revising what was done. So time is equal to t here, and theta 1 is going from theta initial to theta final in that time. So we have to find the position. Okay, so you have to find theta, theta dot and theta double dot. How do you find that? So you divide this time into equal intervals of time. Okay, for example, if this is 10 seconds, just for example, then you divide it into maybe 10 or 100 instance. If I divide this 10 seconds by 100 instance, I'll divide it. What I'll get 0.01. Okay, so 0.1, sorry, 0.1 in units. Okay, so each of this fellow is 0.1 unit. Okay, so this is full is 10 seconds, right? So what I'll do is at every instant of time 0.1, I will take that final equation theta t, okay, theta 1 t, which is a0 plus a1 t plus a2 t squared plus a3 t cubed, and put 0.1 in there. So I get the value of position, velocity and acceleration. Then I take the second instant, I put the value into this equation, and I get the next instant. So in that way, for every instant, I'm going to compute what is theta, theta dot and theta double dot using those three equations. Okay, so this is how I get my position, velocity and acceleration. Okay, so after I get the velocity, position and acceleration, I will take the velocity, position and acceleration and put it into the dynamic equation. That is, I put it into this equation and get my torques. Now what we are going to compute essentially is, so what are we going to compute? We're going to compute the final torques, final joint torques. Okay, in our case it was tau 1, tau 2. Now after that, what we are going to compute, we also want to see, so that is one thing. What you're going to see, we want to compute individual D, H and C components. Okay, so with respect to time, and we want to see variation, a variation of a tau and DHC with respect to time. So what I want to basically tell you here is that as time is going to decrease, inertial forces are going to increase. So we have seen that tau is equal to D into theta, theta double dot, plus H, theta dot into theta, plus C into theta. Okay. This one depends on acceleration. This depends on position, velocity and position, and this depends on position only. That means if you are going very slow, very slow, then a theta double dot is almost equal to 0. Okay, so for example, if the manipulator is moving very, very slowly, that means acceleration is almost 0. Okay, but if you are going very fast, so if you are going very fast, then theta double dot is high. Okay, so if I change my time of motion, you can see the variation of tau, H and C, and that is why I'm going to vary time also. So first we'll do it for different instance of time. For example, we can do for 5 seconds. Okay, that means the manipulator is moving from one end to the other end in 5 seconds. Then I can do for say 2 seconds or 1 second. Okay, and then I can do for very fast 0.1 second. That means it is moving from one point to another point in just 0.1 second, which will mean that it will have very, very high acceleration. So basically what we want to see, what is the variation of torque. So if we vary time, we can see what is the effect of the increase or decrease of acceleration, velocity, and position on the torques and the different components H, C, and D. Now we see that this one, gravity, does not depend on velocity and acceleration. So gravity component will more or less remain constant. Okay, so this does not depend on theta double dot and theta dot. So gravity is constant. So this is something that we'll see, that even if you change your time, it will have no effect on gravity, but on gravity term, on the gravity component rather. But it will have an effect on the acceleration, that is the maximum. Coriolis centrifugal does not have much component, and it is not going to depend. It is not going to depend on the time of travel. Okay. So let's see how we're going to write our program now. So when we're going to write our program in this way, so the first thing in the program. So this is my MATLAB. A MATLAB program for inverse dynamics. Okay, and the problem is the same problem that we talked about, that I had just given some time back. So the lengths are L1, L2. So this is L1, that is L2. Gravity is acting at M1 and M2, which is at half the length. So this is L by 2, L by 2. Okay, and yes, and the parameters also we have written some time back. So it is A1 is equal to A2 is equal to L, and sorry, let's make it L only. Okay, so not L1, L2, let's make it L. Now alpha 1 is equal to alpha 2 is equal to 0, D1 is equal to D2 is equal to 0, and the variables are theta 1 and theta 2. Okay. So the first thing in the program that you have to write is the mass parameters. We have to define the mass parameters as M1 and M2. Okay, so this is how the program would look like. So this is the program. I will show you the actual program in MATLAB. This I'm just giving you the overview of the program. So first we define the mass, then we define the length, okay, as L. Then we define gravity, G is equal to 9.81. Okay, then we define the final position, initial and final positions, initial and final positions of theta 1 and theta 2. Okay, after that we define the time of motion. Okay, so if I draw it here again, so our link is like this. So it is going to start from, let's say, from here. It will go from here to here, and let's say it will come like this, just for example. Okay, so this is my 40 degrees, let's say, that's my 60 degrees. Initially we'll do with this, then we'll change that angle and see what happens. Okay, so and it will go in some time t. Let's say we will check it for 3 times. The first time is going to be for let's say 5 seconds. The second one will be 1 second, and then it will be 0.1 second. Okay, we'll check it for each of this time instance. So for 5 seconds, it means that the links are going to go from here to there in 5 seconds, both of them in 5 seconds. Then it will go in, say, 1 second, and then it will go in 0.1 second. You can just play with that time just to see the variation of the torques. Okay. Next, what do we need to do? We need to compute the polynomial. Okay, so we need to compute the polynomials for theta 1 in terms of time and theta 2 in terms of time. That basically means we have to get the variables A0, A1, A2 and A3. That's what we have to get. Once we get that, then from here what we can do, after we compute the polynomials, we can find theta dot, and theta double dot, position, velocity and acceleration for theta 1 and theta 2. Okay, now at every instant we have to find these values, put it into the dynamic equation and compute what is HCD. So at every instant of time, so I will probably divide the time t total time by 100 units, okay, or less than that. And then for every instant of time, we can find theta, theta dot, and theta double dot, okay, for theta 1 and theta 2 time in terms of time, and then put it in the dynamic equation. Okay, so the dynamic equation is tau h theta, theta double dot plus h theta dot theta plus c theta, right? So when every instant of time, I'll compute the position, velocity, acceleration, put it in there, get the tau, and then I'm going to plot. And what am I going to plot? As I said, that we are going to plot tau 1, tau 2, the joint torques, okay, and then we're going to plot d, h, and c, the different components, okay, different components of tau, and we're going to vary. So this is what we're going to plot for let's say three different time instants. Now why are we plotting tau 1, tau 2? Tau 1, tau 2 will tell you what is the total torque acting at the joint for a particular time of motion. Now d, h, and c will give you the different components that are contributing to tau. Now what we want to see, why are we doing it like this? We want to examine the effect of time, which basically means effect of theta double dot, theta dot, and theta on d, h, and c. Okay, so what I just said is that what I just explained is that the torque at the joint depends on the acceleration, inertia term, Coriolis centrifugal, and gravity term. So if I change the time, what will happen is the acceleration will start varying. The theta remains constant. Okay, so by increasing or decreasing the time of travel, I can change the acceleration, and then I'll have a look at what happens to the d, h, and c components. So this is what we'll plot for the full time. Okay, so now what we'll do is we'll look at the MATLAB program. So the basic MATLAB program is written like this. Okay, so this is the MATLAB program where we are writing, we are inputting the mass, length, gravity, initial and final configuration of theta 1, theta 2, and we are the time of motion. So this I've put as a array of 5 second, 1 second, and 0.1 second. So first it will compute for 5 seconds. Okay, the tau and the DHC. Then it will compute if the travel time the time of travel is 1 second, which means it's faster, and then it'll put the time t for 0.1 second, which is the fastest. Okay, so for each of these three cases, we'll examine and see what is happening to the torque tau 1, tau 2, and what is happening to the different components. So let's look at the program now. So the program looks like this. So let me open MATLAB. So I'll just close this and open MATLAB. Close this and open MATLAB. Okay, so here. So here we are opening the MATLAB window. Okay, I'm using online MATLAB. So what comes out in the first screen is the command. Okay, it's online, so it's a little slow compared to a desktop one. Now, okay, so we are here, and I am opening so I have opened my the inverse dynamics program. So this is the inverse dynamics program, and the way it is written is the way I was explaining it some time back. First, we are going to declare link masses, link lengths, and gravitational acceleration. So m1 is equal to 1 and m2 is equal to 1. So just for simplicity, we are saying that the mass of the links is unit mass. Link length is also unit mass, and gravity is 9.81. Then we define the initial position. So you can see this is the initial position Okay, this is the initial position theta 1. So theta 1 is theta 1, and theta final for 1 is equal to this one. Okay, I hope you can see the cursor. Then we define for theta 2. So theta 2 initial position is 0. Theta 2 final position is 60 degrees. So I'm converting it into radians, multiplying by pi by 180. Okay, so we have defined our mass here. Then we have defined our link lengths here. Then I'm dividing theta 1 initial to theta 1 final. So what I'll do is I'll change this theta 1 initial to theta 1 final and then see what happens also. Now, the time instance that we are keeping is I'm going to compute for 3 different instances of time. So the manipulator will move from 0 to that initial to final for 3 different time instances, and for each of them we will compute what is the dynamic torque and HC and HD and C components of the torque. So I'm putting 3 instances of time. One is 5 seconds. So theta 1 and theta 2 are moving from 0 seconds to 5 seconds, okay, and covering the respective distances. Then 1 second, okay. So the two links are moving in 1 second, and then 0.1 second. So this shows that 5 seconds is slow actually. So you'll see that the acceleration component is pretty slow, is pretty low. Okay, 1 second is faster, so it will be higher, and 0.1 second is extremely fast. Okay, you can imagine a 0.1 second is covering 60 degrees in 0.1 seconds. So what is the speed? Okay, so this is basically to show the variation of these components. Then we are using a for loop here, basically, for calculating the coefficients of the cubic polynomial. So the components of the cubic polynomial are A0, A1, A2, and A3. Now this we have done in the last class, and we solved it that how do you get the actual values. So putting the constraints theta initial to theta final and velocity at initial time to final time, which is equal to 0. Putting those, we get these 4 equations. And you put in the initial constraints, okay, and the velocity constraints into this one, and you get A1, A2, A3 for theta 1, and then for theta 2. Okay, so for this is for theta 1. So A0 underscore is for theta 1. Okay, and A0 underscore 2 is for theta 2. This also has 4 variables, 4 coefficients. Now, using this, we get the equation of the polynomial. Now, once we get the equation of the polynomial, we have to find the velocities, position, velocity, and acceleration. So this is telling us that calculating the joint position, velocity, and accelerations for joint 1. Okay, so theta 1 is the full equation, which is equal to A0 plus A1t plus A2t squared plus A3t cubed. This is theta 1 dot means the position, and this one is the dot dot, which is the acceleration. Okay, this is for joint 1, and this is for joint 2. Exactly the same way what we have learned in trajectory planning. Now, once you find the position, velocity, and accelerations, our next job is to put this in to the dynamic equation. Okay, now the dynamic equation has been written separately here. So the d term is written here. Okay, in the equation I had showed is the same equation. So this d into the acceleration will give you the inertia torque. H term is written here. H term into H term already contains theta and theta dot. So this is the Coriolis term and centripetal term. The third term, the C term here, is the third term here is the gravity term, which only contains theta. So you can see that this contains theta dot dot is there. Okay, so you can see that there is theta dot dot here. So theta dot dot means acceleration, whereas this one has theta dot. Okay, so which is centripetal here. Okay, and this one only has theta, which means gravity. Okay, so summing these 3 are going to give us the total torque. So we are calculating the total torque as d term plus h term plus c term. Okay, which is exactly what we had done. Now we are storing them and plotting them later. So this is for plotting. So how we are plotting is we are plotting your x-axis is your time instance. Okay, so time, whatever is your time we have specified. Then joint torque, it is plotting the joint torque. Okay, time versus joint torque, and then time versus your components, which is shown down here, which is inertia component, Coriolis centrifugal component, and gravity component. Okay, and this is for legend. So this legend is basically for writing what it indicates on the graph. Okay, Then we are initializing the storage variables for the next run, because first run is for time instant of 5 seconds. Okay, then it will have to clear the variables and run it again for 1 second, and then it will clear again and run it for 0.1 second. So for 5 seconds, you'll be getting two graphs. One graph giving us the variation of tau 1 and tau 2. For 1 second, we'll be getting again, for 5 seconds, we'll be getting two graphs. One graph giving us tau 1, tau 2, the other graph giving us H, C, and D components. Okay. Similarly for 1 second and for 0.1 second also. Okay, so this is our program, and this is how you write the program for inverse dynamics. Now let's go to the editor. Something to remember here, keep in mind that time was 5 seconds, then it was 1 second, and there was 0.1 second. So first two graphs will be for 5 seconds, then it will be for 1 second, and then it will be for 0.1 second. So let's run it and see what we get. So it is plotting figure 1, figure 2, figure 3, 4, 5, and 6. So for every time instant, it has two figures. Okay, we'll just see what those figures are. Okay, so here you can see that figure number 6 is variation of joint torque components. Oh, let's look at this one first. Okay, let's look at figure number 5. Should we start from this side? Okay, let's start from, okay, no, it's okay. Let's look at figure number 5 first. Now this means this is the joint torque for tau 1 and tau 2. Joint torque for 1 is the blue one, and the orange one is joint torque 2. And time is 0.1 second. Okay, so this is how the joint torque of the joint 1 and the joint 2 varied for moving the link from theta 1, moving the links by, for theta 1 by 40 degrees and theta 2 by 60 degrees from 0 position. Okay, so you can see the variation of the joint torques for tau 1 and tau 2. Now joint torque tau 1 is much higher because it is carrying the weight of the joint 2 also. Okay, that's why it is much higher. That is clear from here. Now please look at the numerical values. It's about 1600. Okay, Newton meter. So you can imagine what is how high the torque is. 1600 Newton meter torque in the joint to carry only a mass of 1 unit mass, say 1 kg. Okay, so you can imagine how much torque is being required here. Okay, so this is something to note. Now let's look at the figure number 6, which is showing us for the same joint torques, what are the different components of D, C, and G. G is gravity. Okay, so what we are seeing here is, okay, please note that here it is, I had written C, but it is gravity vector is denoted as G here. Okay, now what this is showing us is that the inertia term for link 1 is as high as here. The inertia component rather is 1600 almost. Okay, inertia term for the second one is a little bit lower, it's about 500. Okay, so adding this and this is contributing to the major component of the torque here. The gravity component is as good as 0. Now this is not 0, but because of this scale of 2000 on the y-axis, whatever is the gravity torque, it is almost becoming like 0. It is not 0. Okay, so there is some gravity torque, but it is negligible in comparison to the dynamic, to the inertia torque. Okay, so this is something to note, that the variation of these three. So Coriolis and centrifugal is also there, but it is also much less than the inertia forces. So this is on one end of the spectrum, where we are having the motion for 0.1 second as indicated there, and we are seeing the variation of the torques going from 1600 Newton meter. Now on the other side of the spectrum, and yeah, note this carefully also, remember this, that here you're seeing that the gravity torque is almost 0, and your inertia component is 1500 and 500. Okay, now let's go to the other end of the spectrum and see that for very slow speed of 5 seconds, what happens. So figure 2 is for 5 second travel time of 5 seconds. Now you see that the inertia torque, which is the blue color and the red color, is as good as 0. Okay, so please note this. What I was trying to explain with these graphs is that as you change your acceleration, your torques are going to change and your different components are going to change. So here our gravity component is 20. Okay, so gravity component for first joint and gravity component for second joint, this is 20 and that is 5. So actually the gravity component was about 20 and the inertia component is 0. Why? Because your acceleration is as good as 0. 5 seconds is very, very slow. So it's moving in 5 seconds very, very slowly. Coriolis centrifugal terms are as good as 0. Again, because the velocity is very, very small. Okay. Now gravity term will remain more or less constant. Now let's look at figure 1, which gives us for the total travel time of 5 seconds. If you look at the torque, the components of the torque, the first fellow is 20 and the second fellow is 25. Okay, so that is what is giving us the total torque. Okay, so here it is slightly less than 20. So adding that and this is giving you the total torque, which is 20, and the joint number 2 is 5. Okay, now so this is one end of the spectrum where we have seen that the Coriolis and centripetal and inertia is as good as 0, only the gravity term is there. This is for motion of 5 seconds. Okay, and note the values again. The total joint torque is 20 Newton meter. In case of 0.1 second, what was the total joint torque? It was 1500. So you can imagine what happened. And again, in this case, we saw that our gravity is 20, whereas in this case, the gravity is it is 20 here also because gravity is constant. Gravity components are constant because it depends only on position, not on velocity and acceleration. Okay, but the acceleration torque was 1500. Now let's look at the in-between position where we are having, so let's look at figure number 4. So this was for travel time of 1 second. Okay, you can see very clearly that the gravity torque is constant. Okay, please note here, this is travel time 1 second. Your gravity term is 20 only. Below 20, it's about 18 or 19. Okay, but your acceleration has come up little bit now. So inertia is here now, the blue line. Okay, so it has come up little bit. It was almost 0 for 5 seconds, but at 1 second, your inertia seems to have come up now. So it is showing that it is 15 seconds. It is 15 here now. Okay, 15 Newton meter. So for 1 second, this is the profile. You have gravity torque, which is constant. Inertia torque has increased. Coriolis torque has also increased. Okay, and if you look at the corresponding figure here, so you see that the total torque of joint 1 and joint 2, this is 35 now. In case of 5 seconds, it was 20 only. So in case of 5 seconds, how much was it? In case of 5 seconds, it was 20. Okay, the joint 1 torque, and joint 2 torque was 5 in case of 5 second motion. In case of 1 second motion, your joint 1 torque becomes 35 and your joint 2 torque becomes 10. Okay, why has it become like that? Because your gravity component has remained same. It is 20. It is the acceleration component which has increased. Acceleration and velocity. Okay, so this is what I've been trying to explain, that in terms of dynamics, you have to be careful about the time of travel. So if a system is moving very slowly, then the inertia components are very, very small. You can neglect them. But if it is moving very fast, then your inertia can become extremely fast. Okay. So this is for 1 second. Okay. Now, if you compare again the torques for 1 second and 5 seconds, this figure 3 is for 1 second, it is 35 for joint 1. For figure for 0.1 second, it is 1500. Okay. Now, if you make it slower, it is for 5 seconds, it is only 20. Okay. This is showing the indication. It is indicating the variation of the inertia term, the components, the inertia contribution to the full torque. Now, just for fun, let's make it. Let's change it a little bit, and for example, for the same 40 degrees, theta 1 and theta 2 equal to 60 degrees. So here is 40 degrees and this 60 degrees. I'll just change it just for fun. So we will change it to, let's say this is 120 degrees, and this is let's say 30 degrees. Okay. Now time of travel, let me keep it 5, 1, and so let's remove that 5. Let's remove the 1, 0.1, and let's make it even faster, 0.001. Okay. No, 0.001 is impossible. Okay, theoretically it's possible, it'll still run, but then it'll go, I mean, that's something which is not possible. Okay, so 0.1 second also is not possible. For example, to move 120 degrees in 0.1 second, I don't think any robot can do that. Okay, so this is just to show the variation. So let's, I'll just close these figures. Figure 6 is closed, 5 is closed. Okay, so I close these figures. So what we have done is we have changed theta 1 from 0 degrees to 120 degrees, theta 2 from 2 degrees to 30 degrees, and my time of travel is 5 seconds. Let's not put 5 also, let's put 1 second. 1 second, 0.1 second, and 0.01 second. Okay, now let me run it. So this is my program. Let us run it and see what it does. So the first two is for 1 second, 0.1 second, and 0.01 second. Okay, so 6 figures have come. Okay, so so if you look at figure 4, what is happening is that figure 3, if you see, the torque has gone up to 0.4000. Okay, figure 4 for 0.1 second. Sorry, this is for 0.1 second. It has gone up so much because the angles are, I've changed my angles also. Now for 1 second, so let's see this variation of torque for total travel time of 0.1 second. It is gone up to 3500, joint 1 and joint 2. Okay, now for 1 second, it is 60 Newton meter. Again, it's the same thing. If you look at the components, it will show that gravity is lower, but here inertia has gone up a little bit more. Okay, the blue line has gone up a little bit more. Now, if you look at figure 4 for 0.1 second, inertia has gone up. This is for figure 4. Now, if you look at figure 2, you see that inertia component is only about 35. Okay, gravity is 20. Okay, what about this fellow? This fellow, the inertia is again showing 0 because it's much smaller. Okay, in comparison to 3500 Newton meters. Okay, now in this one, there is a 10 raised to 5 units which has gone up. Okay, so there is a 10 raised to 5 which you can't see. It's coming there. Okay, and if you look here, it is again 10 raised to 5, the unit on the y-axis. You can see it there, but it's just below that writing there. Okay, so 10 raised to 5 units. So it is becoming 10 raised to 5 will mean how much? It's a very, very large number. It's an impossible number for a robot to have that kind of torque. Okay, so this is basically showing how a program, how to write the inverse dynamics program, and how to run the, how to get the torques, and to understand the variation of the acceleration with respect to time. Now, in this program, we could also make it generalized by putting the DH parameter table, writing the generalized matrix, putting the transformation matrices, and then writing this. So that will become a more general program. But with whatever we have done in the last few classes, especially with MATLAB, you should be able to do that now. Okay, so today's class was on the use of MATLAB, and we have seen how to write an inverse dynamics program and how to compute the various terms, H, C, and G terms of the dynamic equation. This also gives a very good example of the use of trajectory planning, that you have to write a trajectory first to find the position, velocity, acceleration, which you are supposed to put in the dynamic equation to get the torques. Okay, so as we go along, we'll be looking at more problems with the MATLAB, where you can actually write your own program